In the second section of the fourth module, we're going to continue looking at risks, this time in relation to chemical health risks and environmental risks of wastewater reuse projects. First, we'll discuss the main health risks to humans from chemical pollutants in treated wastewater. Then we'll discuss environmental risks that may be associated with water reuse. Chemical health risks. Microbiological contamination, as discussed in the previous video, is by far the biggest and most immediate risk to human health. However, the chemical health risks to humans must also be considered and assessed when planning to reuse wastewater. Thousands of different chemicals are used every day in industry, in the home, in hospitals, and other activities such as cleaning. Some of these chemicals may make their way through the wastewater system and into water to be reused. The fact that the sources of this contamination are often diffuse makes it difficult to assess and manage. Attention should be paid to this risk, particularly in developing countries where high levels of contamination from rapidly growing industrial sectors may pose a risk to populations through agricultural reuse of wastewater. It should be noted that the 2006 WHO Water Reuse Guidelines state that for most chemicals, their concentrations in wastewater or wastewater irrigated products will almost never be high enough to result in acute or immediate health effects. The main health risks with chemicals are associated with long-term or chronic effects, for example, cancer, that usually occur only after many years of exposure. We're going to look briefly at several categories of chemical hazards, which are heavy metals, nutrients and indirect health impacts, organic compounds, including antibiotics, which may lead to increased antibiotic-resistant genes, or ARGs, in the environment, as well as endocrine-disrupting chemicals like dioxins and pharmaceutically active compounds, endotoxins and inhalation exposure, and other chemicals of emerging concern, or CECs, such as microplastics. The accumulation of heavy metals in agricultural soils irrigated with wastewater may lead to elevated levels in the edible parts of plants. Such heavy metals include lead, cadmium, mercury, and arsenic. These elements may also accumulate in animals and animal products such as meat and milk. For example, when dairy cows consume feed with high levels of contaminants. These contaminants may also find their way into groundwater that is used for drinking. The geological conditions of aquifers and the presence of heavy metals in rock formations are also an important factor. The wastewater chemistry may encourage leaching of certain heavy metals into the groundwater than would otherwise be the case. Maximum tolerable soil concentrations of various metals are provided in Section 4.6 of Volume 2 of the WHO Water Reuse Guidelines. Part of that table is shown here. It should be noted that the uptake of heavy metals by plants is highly dependent on the soil conditions and the presence of other inorganic elements. The pH of the soil, the organic matter content, the presence of other heavy metals, the application of chemical fertilizers, the addition of lime, ploughing, and water management all have a large influence on the bioavailability of specific heavy metals. For example, acidic soils lead to greater absorption by plants of cadmium and lead than from neutral soils. A 2021 meta-analysis of 95 studies showed that where untreated wastewater was used for irrigation, the mean level of toxic heavy metals, including nickel, chromium, cadmium, lead, and zinc, were higher than the world standard limits, and that concentrations of heavy metals in the soil and the plant's edible parts exceeded allowable limits. High concentrations of nitrate in groundwater used for drinking is associated with methemoglobinemia, a condition also known as blue baby syndrome, some cases of which are associated with bottle feeding of infants, including several infant deaths. Additionally, high levels of nutrients, particularly nitrogen and phosphorus, in water bodies can lead to rapid growth of toxin-producing cyanobacteria and algae. These toxins can cause skin irritation or, if ingested, gastroenteritis, liver damage, and nervous system impairment. In some cases, exposure through contaminated drinking water is thought to be associated with liver cancer in humans. The treatment of excessive levels of nutrients is therefore an important part of wastewater treatment. Certain types of bacteria contain toxic substances within the outer membrane of their cell walls. This toxin is known as endotoxin and is released upon the death of the bacteria and may persist in wastewater if not treated. Even a small amount of endotoxin that is inhaled and finds its way into the bloodstream through the lungs may cause significant illness such as fever, organ failure, respiratory failure, or even death. The chemical compounds of endotoxins are quite stable and resistant to heat, and so boiling does not inactivate them. Specific treatment may be required to oxidize and deactivate them, using hypochlorite or peroxide, for example. Antibiotics are an important part of modern medicine and are used for many different infections. Some of the active ingredients inevitably find their way into the wastewater system, as not all of them are utilized by the body. Some studies show that antibiotics in wastewater used for irrigation may accumulate in soils and be taken up by crops. Additionally, the presence of elevated levels of antibiotics in wastewater may encourage the development of antibiotic-resistant pathogens, either in the wastewater or in the soil, impacting the normal microflora of the soil. Antibiotics, antibiotic-resistant genes, and antibiotic-resistant pathogens may be taken up by plants like nutrients. Pathogens may pass through the natural route and be internalized into the edible part of the crop. This poses a risk for consumers, especially when the crops are eaten raw. The level of treatment effectiveness for the removal of antibiotic compounds and other pharmaceuticals from wastewater is becoming more important in many places around the world. Considering the pathways for contamination and eventual health risk to humans is quite complex. It can also be complicated for practitioners to assess a realistic level of risk in relation to such a hazard. Research on the risks continues and risk assessment methods are being developed. One such journal article shown here provides further reading on the subject. Other pharmaceutically active compounds may persist in wastewater, usually at very low concentrations, in the range of nanograms per litre. Considering most of these compounds require the ingestion of large doses over long time periods to produce a clinical effect, the risk remains relatively low. However, it is an area of continued research and one that remains a concern for health regulators and the public. One category of these compounds that has been studied in more detail is the endocrine disrupting chemicals, or EDCs. However, it is not only pharmaceutical compounds that have the ability to disrupt the endocrine system. These compounds may be found in the contraceptive pill, phytoestrogens, pesticides such as DDT, and industrial chemicals such as bisphenol A. They can have an impact on the structure and function of an organism's endocrine system and cause varied effects, including effects on reproductive function. Antibiotics and other pharmaceutically active compounds and endocrine disrupting chemicals are often grouped as chemicals of emerging concern. Chemicals where the risks are still being researched and understood, such as those mentioned, as well as things like microplastics. These chemicals may come from homes through pharmaceutical and personal care products, including prescription and over-the-counter drugs, veterinary drugs, cosmetics and fragrances, sunscreen products, dietary supplements, and detergents and antimicrobials, as well as from industry waste and industrial products, including industrial chemicals, solvents, and per- and polyfluorinated alkyl substances known as PFAS. As mentioned previously, the eventual risks that these compounds may pose to human health in different circumstances may require further investigation. However, they also pose a risk to the environment and ecosystems into which they are released. Let's now take a look at the environmental risks associated with water reuse. Chemical pollution remaining in treated wastewater that's used for water reuse generally poses a greater risk to the environment than to human health. Microbiological contamination is by far the biggest and most immediate risk to human health and can also pose a threat to wildlife directly and indirectly. If the treatment process has been able to reduce microbiological risk for humans, then it will also generally be minimized for environmental risks. The same chemical hazards identified for human health risks in the previous section also pose risks to certain terrestrial and aquatic plant and animal species, or even to entire ecosystems. The accumulation of these compounds can pose a threat to the environment for many years or decades, such as with PFAS, which persist in the environment and are extremely difficult to break down. Typically, excess nutrients leading to eutrophication of water bodies and heavy metals present some of the most immediate risks to the environment from wastewater. Additionally, one of the major environmental impacts of polluted water is on agriculture, where large areas of land may be affected, leading to severe environmental, economic, and even indirect human health impacts. Wastewater often contains elevated levels of dissolved salts that are difficult and expensive to remove. Hence, it is rare for a water reuse project to invest in lowering the salt level for agricultural irrigation, as it can make the project uneconomic. Accumulation of salt in soils can lead to plant toxicity and severe reductions in crop yields. Once soil salinity problems arise, they are often extremely difficult to treat or manage. Elevated levels of salt and other organic compounds may also lead to losses in soil fertility due to factors such as sodicity, alkalinity, or soil destructuration. Contaminants in wastewater for agriculture may also lead to blockages in irrigation equipment and malfunctioning in irrigation systems due to precipitation of salts or other compounds, corrosion, or algae growth. There are a number of complex factors that may determine the feasibility of a water reuse project where the wastewater contains elevated levels of salt. The existing state of the soils, the type of crops, and their ability to grow in saline conditions, the groundwater interaction with the soils and its salinity content, rainfall, irrigation and soil management activities, such as tilling the soil, crop rotation, and leaving land fallow, as well as fertilizer and pesticide application. The number of factors at play is significant and may require additional expertise and advice from experts such as an agronomist, as well as engagement and consultation with the farming communities or associations, which are likely to have knowledge about the soil and farm conditions and who will be most impacted. For further information about water quality and agriculture, the International Food and Agricultural Organization, or FAO, published its guide online, which contains detailed information on water quality evaluation, salinity problems, infiltration problems, toxicity problems, water quality for livestock and poultry, a specific chapter on irrigation water quality and wastewater reuse, as well as case studies from all over the world, including several from the Middle East and Northern Africa. This report was first published in 1985 and was updated and reprinted in 1995. Even though it has not been updated in some time, it continues to be the main reference document for water quality in agriculture and is referenced in the WHO Water Reuse Guidelines of 2006. Many national frameworks for water reuse focus primarily on health risks, while environmental risks are addressed through other existing guidelines or regulations relating to wastewater discharge to the environment. The Australian Guidelines for Water Recycling, released in 2006, contains some detailed information on environmental risks and identifies the following key environmental hazards in recycled water, which are boron, chloride, sodium, cadmium, and chlorine, which are all toxic to plants in large quantities. Chlorine is also dangerous to aquatic organisms, and sodium excess can cause soils to become sodic and can degrade soil structure, making it difficult for water and plant roots to penetrate the soil. Salinity, phosphorus, and nitrogen all pose problems that we've already mentioned. And finally, waterlogging or excess water, which can raise the groundwater level and potentially cause soil salinity. Chapter 8 of the second volume of the WHO's 2006 Guidelines on Water Reuse also contains detailed information on environmental risks at varying concentrations of certain parameters for agricultural reuse. This information can be found in Table 8.1, a part of which is shown on the screen now. We can see that some levels of certain parameters, such as phosphorus, can have no effect or even increase productivity, whereas higher levels may lead to negative effects. Pause to read in more detail. As mentioned, salinization of soils and groundwater is one of the most difficult problems to manage. Many places around the world have experience with this issue. Israel has a very high rate of water reuse for irrigation and has long battled with salt issues in such an arid region. The government implemented a salt control program during the 1990s to reduce the concentration of salts entering the wastewater system at the source. Affecting change at the level of consumer products and limits on industrial discharges was estimated to be much cheaper than trying to remove salts at wastewater treatment plants. The program saw a reduction of chlorides in wastewater from 120 milligrams per litre in 1992 to half that in 2002. Some end uses for water reuse require very low salt levels, as well as water reuse in some sensitive environments. For these limited number of situations, reuse water is treated by reverse osmosis to remove salt. The salt control program was implemented progressively over around 20 years. During the 1990s, the government introduced some minimal requirements and regulations, as well as some non-mandatory guidelines and requests to industry. Stronger limitations and standards were introduced progressively throughout the decade. Actions included guidelines for controlling salt discharge from slaughterhouses in 1995, and in 1998, a complete ban on industrial discharges of brine to sewer. One of the most important chemicals to target was boron. Starting in 1999, the limit for domestic and industrial detergents was progressively decreased from 8.4 milligrams per litre to 0.5 milligrams per litre in 2008. Educating the public on the salt content of dishwashing and other detergents was also an important aspect of the program to achieve purchasing behaviour change.